everyone. We are starting our next unit on exponential functions. So this unit tends to actually be a smaller unit that I do right at the end of the year before your Regents exam. We don't go too deep into exponential functions. You will when you take Algebra 2 and if you take Algebra 2. But I like to expose you to it, and there are some questions on the Regents about it. So we are going to cover it, and we'll cover the basics of it, obviously, since we aren't in school together. So if you recall, I told you guys that we have three worlds that we kind of study in algebra. I know it's cheesy, I call them worlds, but hey, stick with me. We have linears, quadratics, and now exponentials. So linear is our first world that we spend a lot of time in Algebra 1A and 1B. If you remember in ninth grade, we only focused on linear functions. We were focused on solving them. We focused on graphing them. We focused on inequalities with them. We focused on word problems and systems and so much more. So linear would be something like this, 4x plus 1. Okay, then you come back as 10th graders and we review everything for the first half of the year. Then we jumped into quadratics. And quadratics, if you remember, we learned how to factor them. Then we learned how to solve them. We did a little bit of word problems with them. And then we were just getting into graphing, and that's when the school closure happened. Actually, no, we didn't even get into word problems. We were going to get into word problems, but then the school closure happened. So that's something, if you remember, that's like this. And we learned slide and divide and difference of two perfect squares and all those methods to factor and solve it. Now we're going to jump into our last world, and this is the exponential world. And that looks something like this. The exponent is our variable. X is now in the exponent. This, again, we touch on, and is leading you up to Algebra 2. So we shut the door here on Algebra 1. We'll do a little bit in the exponential world, and you'll pick it up in Algebra 2. So let's look at exponential. An exponential function is in the form y equals a b to the x, where a is the y-intercept. So that would be the first point that we could graph. We were going to graph them. B is the base, or what we call the multiplying factor. Okay. So let's just review some of these. Let's see what if the following are linear, quadratics, if they're square roots, if they're cube roots, if they're absolute function, value functions, or if they're exponential functions. So let's start with linear. That was the first kind of equation that we solved. Linear is something like this. You just have an x. Oops. Let's scroll so you guys can see. Quadratic, if you remember, is something to the x squared. Oops. So this would be our quadratic. A square root. Now, you might get a little tricked here because that looks like a square root and that looks like a square root. But this one is actually our square root. This is what we call a cube root because it's to the third out here. Oops, I just kind of blocked it so you can't even see that. This is our cube root. Absolute value is down here. These are what we call absolute value bars. That's our absolute value function. And our newest one to the family here is our exponential function. And that's because our x is now in our exponent. Oops, making it very hard for you guys to see those. Is now in our exponent spot. All right, we're going to do some examples here today. So the biggest thing we're going to focus on today is what makes something linear versus exponential. So, actually, let me explain something quick. Linear versus exponential. Linear functions have a constant average rate of change, which what that means is as you go from one point to the next, you go up the same amount. So let's erase this and let's look at it a little bit better. We're going to go up 1 over 1, up 1 over 1, up 1 over 1. So same amount every time. Linear, you add or subtract to get to your next value. And we're going to look at some tables and see what that means. Exponential, you may have heard the word exponential before. If someone says, oh, that's growing exponentially. Exponential may start out low, but it picks up and goes up like that. Or it can go down like this, just like a line can be negative as well. Exponential, you multiply or divide to get to the next number. Now, I want to explain and show you in terms of something that is pretty relevant to our lives right now, a virus. So we won't talk about coronavirus, we'll just say a virus. So let's look at this. Exponential versus linear. For linear, you add or subtract to get to the next number. Let's talk about a virus here. Let's say that the virus is spreading based on a linear pattern. That means you would add or subtract, but since we're spreading, we're going to add per day. So let's say day 1, one person has the virus. Day 2, we'll add 2 more people get the virus. So when you add 2 to that, you get 3. Day 3, well, since it's linear, it has to go up the same amount each time. 2 people will get the virus. Now 5 people have the virus. Day 4, 2 more people get the virus. So now 7 people have the virus. Day 5, 2 more people get the virus. So now 9 people have the virus. Now let's look at exponential. And this is why sometimes when things grow exponentially, it can be a little scary because watch the difference here. So this is exponential. Day 1, one person has the virus. Day 2, since it's multiplying, we are going to double it or times it by 2. 2 people have the virus. Day 3, well, since we times it by 2, now we're going to times it by 2. 4 people have the virus. Day 4, times it by 2, 8 people have the virus. On day 4, we've already surpassed the linear function. Day 5, times it by 2, 16 people have the virus. All right, we're starting to see a big difference here. 9 versus 16. Let's go a little bit further. Day 6, we'd add 2 here. 11 people have the virus. Day 6 here, times that by 2. 32 people have the virus. Now we're starting to see a big difference. Day 7, times that by 2, 64 people would have this virus. We're not saying this is coronavirus, we're just saying a virus. We are here on day 7. Only 13 people would have the virus. So exponential functions grow much faster than a linear function would. And that's what makes things a little bit scary. So that, say with this coronavirus, if we are spreading at an exponential rate, it's spreading much faster. And that's what makes it a little bit hard to control. Because if you notice here on day 7, this is, again, this isn't the coronavirus model, but day 7, 64 people had the virus that I made up, or 13 only had it in this one. All right, so let's look at some examples here. Number 1 says, explain why the table below represents an exponential function. Well, I told you exponential, you multiply or divide to get to the next number. So you look at this table here. 3 to 6. How do you get to 3 to 6? Well, let me try adding plus 3. If I add 3, will I get to 12? 6 plus 3 is 12? No, that's wrong. So we try to make it exponential. 3, oops, times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. And 24 times 2 is 48. So it is exponential because there is a multiplying factor of 2. All right, let's look at number 2. The two tables below represent two different functions. State which one's linear, which one's exponential, and explain why. All right, so let's try here. 5 to 10, well, I can add 5, but is 10 plus 5 20? No. 20 plus 5 is not 40, and 40 plus 5 is not 80. So let's try to see if it's exponential. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40, and 40 times 2 is 80. So table 1 is exponential because we always say there is a multiplying factor sorry, I'm talking faster than I can write, factor of 2. We always use this word for exponential, multiplying factor. Now table 2 is then linear because, now let's see, 8 to 11, what do we add to get there? 3. 11 plus 3 is 14. 14 plus 3 is 17, and 17 plus 3 is 20. So because we added, it's linear. Because we multiply, it's exponential. So table 2 is linear because there is an average rate of change of 3. So we use average rate of change when it's linear. When it's exponential, we say there's a multiplying factor, which makes sense because we multiply or divide for exponential, add or subtract for linear. And the last example here that I'm going to do with you, and then you guys are going to have a chance to do, I think there's 5 problems for you to do on your own. Which situation could be modeled as a linear equation? If you double something, you're multiplying. If you take a fraction of something, you're dividing. So let's look at our examples here. The value of a car decreases by 10% every year. If you see percentages, that's always a key that it's exponential. So this is not linear. The number of fish in a lake doubles every year. Well, doubling something's really multiplying it by 2, so that's not linear, that's exponential. 2 liters of water evaporate from a pool every day. Okay, so we're subtracting 2 liters of water from the pool every day. That sounds linear to me, but let's check number 4 out. The amount of caffeine in the person's body decreases by 1/3 every 2 hours. Number 4